Hello again, everyone, and welcome to our third Ice Day video. In this one, we're going to take a look at a cool reaction of carbonyls that has an unforgettable name. If you saw the first Ice Day video from earlier today, you'll recognize this AI-generated image and remember how a certain molecule in carrots, namely beta-carotene, is critical for vision in mammals like us and this cute little bunny. And in the second Ice Day video from earlier today, you learned why geminal diol formation explains how chromic acid can oxidize an aldehyde to a carboxylic acid. In this video, we're going to talk about how you can convert the carbonyl group of a ketone and aldehyde all the way to a CH2. Now, you've never seen anything like this before. We're going to take a C double bond O and turn it all the way into two single bonds to hydrogen. There's two ways to do this. The first is an acid, and it's referred to as the Clemmensen reduction. Now, you are not responsible for this mechanism, and it involves relatively harsh conditions. The bottom line is that if you take a ketone or an aldehyde and you react it with zinc amalgam, which is this complicated structure you make with zinc and mercury, and you throw in concentrated HCl, not just a little, this is strong acid, you will absolutely remove the carbonyl and turn it into a CH2 group. The thing to know, though, is these are such harsh conditions that you can't use this reaction with acid-sensitive groups like tertiary alcohols. Remember that tertiary alcohols in the presence of acid will dehydrate to give alkenes. That's from last semester. So although it's important that you hear about this reaction, the Clemmensen reduction, we're not going to spend a lot of time talking about it, but it does take a carbonyl and turn it all the way into a CH2 group. That was an acid. In base, there is a different reaction called the Wolff-Kishner reduction. And in that reaction, we take this carbonyl group and also turn it into a CH2, but notice we're doing this in base. And so in your molecule, if you have acid-sensitive groups like that tertiary alcohol, you can use the Wolff-Kishner reduction. And besides, it has a real cool mechanism. So let's take a look. Okay, the first part of the Wolff-Kishner reduction mechanism is that we're going to add hydrazine. Now, I didn't say it, so let me go back and cover this. This is hydrazine right there. We're going to have hydrazine, and we're going to have highly basic conditions because of the KOH. So if you remember when we talked about imine formation, you'll remember that not only amines, but also these hydrazines could undergo the exact same reaction, and it involves several steps. I'm not going to take you all the way through it, to create an imine analog that is called a hydrazone. And in that molecule, we now have a C double bond N, just like we did in the imine. So this is the identical mechanism to the imine formation. Okay, so we've got this hydrazone molecule. The question is, what's going to happen next? Well, we are in strong base. So what's going to happen is we are going to deprotonate one of those hydrogens off the terminal nitrogen. And the reason that's a reasonable thing to do is that what we generate is resonance stabilized. So we start with the negative charge on nitrogen, but you can move the bonds around pretty quickly so that you can put that negative charge all the way on carbon. So by doing that, you can delocalize that charge. That stabilizes this anion. Some people call it resonance stabilized. We can call it charge delocalization stabilization. There's a pi way there. However you want to think about it, this anion is a lot more stable than you might have thought. So taking this proton off in that first step is really not as strange as it might have first appeared. Okay. So what's going to happen next? Well, if you notice, in particular, this contributing structure, that carbon is extraordinarily basic. So what we're going to do is we are going to put a proton there. And when we do that, we've now put one of the hydrogens in the place where we originally started with that C double bond O. So you can see we're halfway there. We get to this intermediate, which is now neutral. And the question is, what's going to happen? Well, the answer is the same thing that happened before for essentially the same reason. But you're going to see there's a big surprise coming in this mechanism. Like I was saying, this is a cool mechanism. So watch what happens. Well, we're going to take another proton away. And when we do that, we generate this intermediate. Now, I could draw some other contributing structures here, but I don't need to. Because this intermediate is one for the books. This is one that is set up to do something that is ultra cool. In other words, we're going to make a really stable molecule. So it might be a bit of a surprise, but this is one of those few reactions that when you look at this intermediate and say, well, what can happen here? Sure, this site is basic. But if we add a proton there, we just go back to where we were, where we started with that proton. So that's not going to happen. What does happen is we generate an incredibly stable molecule. We do that by eliminating, believe it or not, nitrogen, dinitrogen, a gas, a very stable species. So this entire reaction is pulled through because we are able to generate this incredibly stable molecule, and that drives this entire process. That's the only explanation for why we've made something this reactive, a carbon with a full negative charge. That's not something you've seen before. There's no stabilization there. That is a full-blown negative charge, only possible because we made this incredibly stable nitrogen gas, which just bubbles away. Well, that carbon with the negative charge is an incredibly strong base. So what we're going to do is we are going to add a proton and end up with our final product. So in that final product, we've replaced what was a carbonyl with two single bonds to hydrogen, and we've regenerated our base molecule. So the key recognition element here is a pretty simple one. There's now a CH2 group where there was a carbonyl of a ketone or aldehyde. And it's all driven because we're making nitrogen gas. Now, this reaction is called the Wolff-Kishner reduction. So I couldn't resist. I had to make another AI-generated image so you will never forget this reaction and what it does. So here it is, and I'll just let you look at it for a minute. So one of my former TAs brought this to my attention, that when you think of the Wolff-Kishner reaction, you can think of a ketone as having a little head on it, and that the big bad Wolff-Kishner is going to bite its head off and create an alkene. Either way you want to remember it, the Wolff-Kishner reaction is a really good way to take a carbonyl all the way down to an alkane or a CH2 group. I hope this was helpful.